Hello, my dear students. The topic of discussion of this lecture is the equivalence between basic feasible solution and extreme point of the feasible set of a given standard linear programming problem. I have mentioned on the last lecture and also in previous few lectures that the results that I am describing started from the last lecture. Those are from those are for standard form of an LPP. Fine. So it is our standing assumption that we are considering the standard form of the linear programming problem and then we are proving the results. So in this lecture, we will prove our long waiting result, that is a basic feasible solution is an extreme point and vice versa. Let's start. The first result is the forward part, that a basic feasible solution is an extreme point. So to just write it, so I'm neatly writing the result as a theorem which states the following, that a BFS to an LPP corresponds to an extreme point of the feasible set. The proof is as follows. So let's suppose x bar is equal to x1 bar. X bar has components, n many components, and x bar is a basic feasible solution of the LPP. So let us suppose the components of x bar are x1 bar, x2 bar, so on, xn bar be a basic feasible solution to the LPP. Fine. And this basic feasible solution to the LPP, by that I mean to the constraint set. That means ax equals to b together with x greater than equal to 0. Fine. And once you are considering one basic feasible solution corresponding to a basic feasible solution, you have a matrix, you have a submatrix of submatrix B, capital B, of order m by m, which is a submatrix of the matrix capital A, corresponding to which you consider the basic variables xb, then non-basic variables x and b, you put x and b is 0, and then you obtain the basic feasible solution. The way of getting a basic feasible solution I have mentioned. So corresponding to a basic feasible solution, obviously there is an m by m submatrix capital B of the matrix A, which is non-singular. Capital B is non-singular. A non-singular submatrix of order m by m exists corresponding to a basic feasible solution. So suppose now B is the m by m non-singular submatrix corresponding to the basic feasible solution x bar. Fine. And once you are writing in this way, that B is the non-singular submatrix of A corresponding to the solution x bar, the usual denotation of x bar is xp, that you all know, and accordingly we write accordingly means according to the notation capital B submatrix corresponding to x bar, we write x bar by x bar has n many components, and here usually x bar are presented by column vectors, any vector in the n-dimensional Euclidean space, is to be presented by a column vector, then only this ax will be compatible, this multiplication capital A with x, because A is of order m by n and x, if x is of order n by 1, then only the multiplication of A and x will be compatible. So x is a column vector. We write now x bar by xb and xnb, and xnb components are all zeros, that you all know. Accordingly, we write x bar is equal to, accordingly we write x bar is this, where xb is equal to, let me write here bar, as I put it here bar for x, so xb bar is equal to b inverse into small b. Fine. Now here also, let me for my convenience of writing the proof very neatly, let me suppose capital B is having, capital B submatrix of the matrix A means columns of capital B are m many columns of capital A which are linearly independent, because capital B is a non-singular submatrix, so its columns must be linearly independent, and the columns of capital B are columns m many columns of capital A. Fine. So without loss of generality, let us suppose capital B consists of first m columns of the matrix capital A. If some of them are not just first m, then you just change the role of the variables and accordingly change the denotation of the columns, and then you can write without loss of generality that capital B consists of only the first many columns. So just by changing the roles of or denotations of columns, you can write that A1, A2, A3, AMs, the first m columns of capital A are linearly independent, and there exists at least a set of m many columns of the column capital A which is linearly independent, because the rank of the matrix capital A is equal to m. Fine. And therefore there exists at least one set of m column vectors of the matrix capital A which is non-singular, and with those m columns I am considering that this capital B are these A1, A2, A3, AMs. Fine. So corresponding to any basic feasible solution, you have at least one set of m columns of the matrix capital A, such that corresponding to the matrix consisting those columns, you will have the solution x bar as a feasible solution, and that will be a basic feasible solution. Fine. So here, if you are facing a little bit problem with all these notations, please please revisit the lectures, like lecture number 2, 3. Those lecture in those lectures, lecture number 1 even. So in those lectures, I have explained in detail what are these A1, A2, A3, AMs, and so on. The matrix capital A has columns A1, A2, AN, n many columns, and several of you might be having a problem of understanding linear independence. I do not know whether you have done the mathematics 2 or not. If you have not done mathematics 2 at IIT BHU, then you have to go through a few topics of linear algebra. Otherwise, understanding this linear programming problem will be difficult. And those topics are linear dependence of vectors. Let me write here a few topics. And otherwise, understanding of linear programming problem will be very much difficult. For the course operations research, the prerequisite is mathematics 2. Without learning linear algebra, understanding linear programming problem will be very much difficult and rarely possible. And the concepts from linear algebra is a part of mathematics 2. The concepts of linear algebra which we require to discuss linear programming problem are very few. Those are the concept of linear dependence, linear independence, basis, then replacement theorem, and one more is extension theorem. You please have a look of this concept, linear dependence of a few vectors, then try to revisit the concept of linear independence of few vectors. Then what do you mean by a basis of n-dimensional Euclidean space? Then go through the result of replacement theorem. Given a basis, how you can replace a particular element of the basis, particular vector of the basis by some other vector. That is the concept in the replacement theorem. And in the extension theorem, given a set of vectors from the n-dimensional Euclidean space, how can you extend the given set of vectors to a basis of the n-dimensional Euclidean space? That is the topic of discussion in the extension theorem. Fine. So these few topics you have to understand well from linear algebra. Otherwise, understanding linear programming problem is very much difficult. So I would just request all of you, if you have not done mathematics 2, then please Google these concepts: linear dependence, linear independence, then basis, replacement theorem, and extension theorem. Learn them, play with them a little with some examples, and then get back to the lectures. Otherwise, it will be difficult for you to understand. The prerequisite of operations research, this course, is mathematics 2. Without learning mathematics 2, the topic linear algebra and mathematics 2, this course is not for you. Anyway, now we now get in that. So here capital B is m by m non-singular submatrix of A corresponding to the solution corresponding to the basic feasible solution x bar. Now what do we have to prove? We have to prove that the point x bar is an extreme point. Fine. So we'll prove this result by the method of contradiction. If possible, let x bar is not an extreme point of the feasible set. Fine. If not an extreme point, then obviously then there exists a pair of points which are feasible solutions or feasible points u v. There exist feasible solutions u v with u not equal to v, such that x bar is a convex combination of the points u and v. So lambda u plus 1 minus lambda v, where lambda is some real number in between 0 and 1. Fine. Now you notice the following, very interesting, that this x bar is a basic feasible solution. So all the components of x bar are non-negative, right? Similarly, here you notice that u and v are feasible solutions. So all the components of u and v are non-negative. Fine. And here this lambda 1 minus lambda, those are also non-negative quantities. And once you have this, then in this x bar, you notice that you have precisely in xb bar, how many components are there in xb bar? Xb bar, you have precisely m many components, and here in 0 you have precisely n minus m many zeros, right? In 0, by this 0 I mean 0 vector, n minus m times 1. This is the order of this 0, and m by 1 is the order of this x bar b. Fine. And therefore on the left hand side of this x bar, precisely first m many components of x bar are greater than equal to 0, and rest of them are all zeros. Fine. And on the right hand side, the components after the mth component, those components are all positive. Is it possible? All components are non-negative. Fine. After the mth component of this expression on the right hand side, after the mth components, all components are non-negative. On the left hand side, the components after the mth component are all 0. That is possible only if the right hand side, in the right hand side, all the components after the mth component are all zeros. And if that is true, then what are the m components after mth components? So here you have, for you have u1 u2, then till um, then plus 1, then you have un, and here in v you have v1 v2 vm, then you have vm plus 1 till vn. And if you take this lambda u plus 1 minus lambda v, and if I just consider the m plus 1th component, let's suppose, for instance, I'm considering the m plus 1th component on the right hand side, it will be lambda u m plus 1 plus 1 minus lambda vm plus 1. But on the left hand side, the m plus 1th component is 0. So 0 equals to this. So if this is equals to 0, then what does it imply? Here this lambda is positive, 1 minus lambda is positive due to this, and um plus 1 is greater than equals to 0, vm plus 1 is greater than equals to 0. So this is possible only if um plus 1 and vm plus 1, both of them are zeros, right? And this is true for any of the components from the m plus 1th to un. So from this equation, x bar equals to lambda u plus 1 minus lambda v, you have the following, that that so we write as first x b, sorry, x bar is equal to x b bar, m many components in x b bar, then n minus m many zeros, and you have u greater than equals to 0, v greater than equals to 0, and also you have lambda is in between 0 and 1. We have that as this and this, u and v will be of the form, the vectors u and v of the forms that u has first m many components u1 u2 um non-negative, but rest of them are all zeros. Fine. And v also, and also v is having first m many components v1 v2 vm. They may be, some of them may be 0, but after the mth components, all the components are zeros. Fine. Once you have this, then you note the following, as x bar uv are feasible solutions of ax equals to b together with x greater than equals to 0, what you will have is that ax, you will have ax equals to b, au equals to b, and also av is equal to b. Fine. And once you have this will now imply a times x minus u is equal to 0, and also you will have a u minus b is equal to 0, right? But what is a times x minus u? X has first m many components non-zero. greater than equals to 0, but rest of the m many components are equal to 0. And the matrix capital A is this matrix. The first column is A1, second column is A2, and the nth column is AN. And what is AX? AX is, if I write in the matrix form, then for the first column A1 into X1, A1 into, if I am having components X1, X2, Xn here, AX if I am writing. So here is X1, X2, dot dot Xn. Here X1, X2, Xn, those are the components of the variable X. And here these are vectors. A1 is the first column vector, A2 is the second column vector of the matrix A, and AN is the nth column vector. So AX is A1 X1 plus way up to AN Xn. But here you notice that from the mth component of X bar, from the mth component of X bar, and from the mth component, from the mth component, from the m plus 1th component of X bar, till the nth component of X bar, all are zeros. Similarly for U and V, the components from the m plus 1 to n, those are all zeros. So this A into X minus U is a vector. X bar is a vector of n many components, U is a vector of n many components, and therefore this A times X bar minus U will be given by A1 times X1 bar minus U1 plus A2 times X2 bar minus U2 plus likewise way up to A M X M bar minus U M, right? And therefore and therefore this is equal to, and rest of the elements are all zeros here, fine. In the multiplication of A into X bar minus U is equal to 0. And also from A into U minus V, you have A1 U1 minus V1 plus A2 into U2 into V2, likewise way up to AM UM minus VM, then plus AM plus 1 into 0, because UM plus 1 minus VM plus 1, those, that is 0, and therefore it is equals to 0. UM plus 1 till the nth component is also 0. So this is equal. Now from here what do we get? As this vector, as this set of vector A1, A2, AM, this set of vector is linearly independent, since this set of vectors A1, A2, AM is linearly independent. What will you have? Why linearly independent? Because these column vectors A1, A2, A3 till AM is a non-singular submatrix of A, and therefore the column vectors of capital B are linearly independent. And once it is linearly independent, then these scalars which are multiplied to A1, A2, AM, all these scalars are 0. Fine, that is the definition of linear independence of a few vectors. So this will now imply x1 bar is equal to u1 bar, and this is true for every I equals to 1 to till m. Similarly, ui is equal to vi for all I from 1 to till m, and hence this is implying x bar is equal to u is equal to v. And then what is coming off? You notice that you started with 2 points u and v which are not equal, and x bar is convex combination of u and v, and from there what have you obtained? You have obtained that u cannot be v, and hence there is a contradiction. And contradiction to what? And why contradiction is arriving? Because of your assumption that x bar is not an extreme point you have assumed. which is contradictory. To u not equals to b, and hence our assumption was wrong. X bar is then an extreme point of the feasible set, right? Okay. Now next let me prove the reverse result, that an extreme point is a basic feasible solution. That any extreme point of the feasible set of an LPP by the time in standard LPP is a BFS of the feasible set. That means BFS of AX equals to B together with X greater than equal to 0. How do we prove it? The proof will be as follows, that so let's start with an extreme point. So let us start with an extreme point. So I just consider a point which is an extreme point. So let X bar, or let me say X star. X star is an extreme point of X star is an extreme point of the feasible set of AX equals to B together with X greater than equal to 0. And in X star you may have a few components 0, a few components non-zero, but non-zero components will be all positive because of this restriction X greater than equal to 0. Fine. And X star is an extreme point means X star is an element of this convex set AX equals to B X greater than equal to 0, because extreme point definition is a definition for a convex set, and extreme point is an element of the convex set. Fine. And therefore here all the components of X star are non-negative, so some of them may be 0 also, right? Some of them, maybe all of them are positive, but some of them there is a possibility that some of them will be 0 also, right? So I'm taking the general case. So I'm letting that the components which are not 0, I'm by interchanging the role of the variables, I can push all the non-zero components as first few variables. So I'm letting them that X star, the first component is non-zero, second component is also non-zero, and there are precisely p many components which are non-zero. Xp is non-zero and rest of them are all zeros. Fine. So here you have precisely n minus p many, and this is a column vector. I am transposing this row. And here notice that you may feel ki why only the first few variable components are non-zero. Let's suppose first fews are not non-zero. Let's suppose the second component is non-zero, and then let's suppose second component is 0, third component is also 0, the next the fourth component is non-zero. Then interchange the role of x2 and you name x2 as x4, x4 as x2 in your problem. Fine. And then you will note that at the second place then you will have x4 and x4 is non-zero. So in this way you just keep interchanging the roles of the variables, and in that way you can push the non-zero values in the front and then the zero values at the rear. Fine. And so this is without loss of generality and assumption that first few components are non-zero. Fine. So here you have p, then you may have all of them are also 0. So p is greater than equal to 0, less than equals to m. Less than equals to how many? N many. Fine. So the p can be, maybe none of them is non-zero and maybe all of them are non-zero. Fine. So p is in between 0 and 10. Now here you notice that as you have assumed x star is an extreme point, so x star is indeed satisfying ax equals to b and x greater than equals to 0. Once this is so, then evidently you have ax star is equal to b and also x star greater than equals to 0. That is, you have then, here you notice that the columns of capital A are A1, A2 till AN, and therefore ax star will produce you A1 x1 plus A2 x2 plus, in x star you have first p many variables non-zero and rest of them are 0. So this expression will end up at apxp is equal to b together with all these xi's are greater than 0 for all I is equal to 1, 2, 3 till p. Fine. Okay. And once you have that, we will show the following. Now what do we have to show here? We have to show the following, that you have assumed x star is an extreme point. We have to show x star is a basic feasible solution. So we have to show that the variables which are associated to the non-zero components of x star, they are linearly independent, and that will prove that x star is a basic feasible solution. Because to construct a basic feasible solution, what way do you all follow? The way to find the basic feasible solution, or the definition of basic feasible solution is that you are assuming the rank of capital A is equal to m, and then you are taking up a non-singular submatrix capital B of order m by m of the matrix capital A, and then you are constructing bxb is equal to small b, then you are filtering out xb is equals to capital B inverse small b, and that is the way of finding a basic feasible solution. And corresponding to any basic feasible solution, you have that once a solution given to you, then that is a basic feasible solution if corresponding to the non-zero components of the solution, the column vectors of capital A are linearly independent. Fine. If you can prove this, that the non-zero components of some solution, corresponding to them the columns are linearly independent, that will prove that the solution is a basic feasible solution. Fine. So let me now show that. So what do you have to prove? Required to prove. So to prove here that to prove that x star is a basic feasible solution, we need to prove specifically that there exists an m by m non-singular submatrix of the matrix A such that Bx star is equal to small b. Fine. And that will prove that x star is indeed xb, and then that proves that x star is a basic feasible solution. So how do we prove it? Let us at first pick up the column vectors of capital A which are associated to the non-zero variable of x star. Fine. And we at first show that those columns associated to the non-zero components of x star are linearly independent. If you prove that, if you wanted to prove, then what do you have to prove? You have to prove that these columns A1, A2, AP is linearly independent. Now you can think of capital B is a matrix consisting A1, A2, AP, but here is a chance that P is less than equals to P is strictly less than M. But here once we prove that A1, A2, AP is linearly independent, that will prove that P is indeed less than equal to M, because you know that any set of vectors which is consisting m plus one number of or more than m many vectors, a set which consists more than m many vectors of Rm is linearly dependent. For instance, I consider three vectors in R2, A1, A2, A3, which are from R2, all of them are from R2. This set is linearly dependent. Fine. So any set of vectors, so let me just write it here. Any set of m plus 1 or more than m many vectors of Rm is linearly dependent. This is a very interesting fact which was proven in linear algebra in your mathematics too. And therefore, if a set is linearly independent, that has, if a set of vectors from Rm is linearly independent, then that set consists at max m many vectors. So if you prove that A1, A2, AP, this set is linearly independent, that will prove that P is less than equal to M. If P is equal to M, then you construct capital B consisting only these many columns A1, A2 till AP. Because P equals to M, and all these A1, A2, AP are vectors from Rm, because the columns of capital A are M vectors from Rm. Therefore, these A1, A2, AP are Rm vectors having m many components, and therefore the matrix capital B, if you are constructing by these vectors A1 as the first column, A2 as the second column, AP as the pth column, that will be one m by m matrix. AP is equal to M, and that is a non-singular submatrix of capital A, and that will construct that x star then a basic feasible solution. But in capital B, if you in this A1, A2, AP, if you have P less than M, then in that case you just extend this set of vectors by the extension theorem of basis, that extended set is linearly independent and still a basis of Rm, and that will construct the matrix capital A. Fine. So all these things, the discussion, to understand well, you please note that you need to have a neat idea about these concepts: linear dependence, linear independence, basis, replacement theorem, and extension theorem. Please have a look on those concepts and then come back to this discussion. But I am writing down whatsoever I have said so far. I am writing down very neatly so that you will not miss any of the word that I have spoken so far. So let me just try to write very neatly that at first we saw that the vectors a1, a2, ap, this is linearly independent. Then with the help of a1, a2, ap, we'll construct a submatrix capital B, and that submatrix is linear non-singular submatrix of capital A. And from this capital B, we will be able to identify that the point x star is a basic feasible solution. Fine. So let's start. So here we'll prove that now the set A1, A2, AP, which are columns of capital A associated to the non-zero values A1, X1, X2, Xp. We prove that this is linearly independent. If linearly dependent, on contrary, let us assume that A1, so if possible let A1, A2, AP is linearly dependent. If possible let this is linearly dependent. If this is linearly dependent, by the definition of linear dependence, then there exists scalars lambda 1, lambda 2, lambda p with at least one of them non-zero. This is definition of linear dependence of a set of vectors. Then there exists a lambda 1, lambda 2, lambda p with at least one non-zero lambda I, such that by lambda I mean I is ranging from 1 to p, okay, or lambda j, let me write, because I'm keeping the index I for I equal to 1 to m or I equal to 1 to p here, fine, such that you have lambda 1 a1 plus lambda 2 a2 plus lambda p ap is equal to b. Sorry, not b, very sorry, equal to 0. That is the definition of linear dependence. Okay. Now from here we will construct that the extra will by this equal to 0, we will be able to show that x star cannot be an extreme point, and that will then prove that this set is linearly independent. Fine. Now how? So let me now try to construct a pair of points whose convex combination is the point x star with the help of this equation. Once this equation is valid, now you with the help of these two equations, here you have one equation 1 and here you have equation 2. By these two equations, let me construct a pair of points whose convex combination will produce the point x star. How can you show this? So you notice that from 1 and 2, from 1 and 2, we have for any beta, a constant, any constant greater than 0, we have the following, that I take a1. So what I am doing is I am taking the equation 1, then I am multiplying equation 1 plus 2 into beta. If I am doing, then you will get a1 into x1 plus beta times lambda 1 plus a2 into x2 plus beta times lambda 2 plus so on, then ap xp plus beta times lambda p is equal to b. Then next I am doing 1 minus 2 into beta. The equation number 1 minus beta into the equation number 2. If I am doing, then I am getting a1 times x1 minus beta lambda 1 plus a2 times x2 minus beta lambda 2 plus so on ap times xp minus beta lambda p is equal to small b. Fine. And now here you notice the following. We have this, and then we let you construct two vectors u and v as follows. u u is having the first component as this x1 plus beta lambda 1, second component as x2 plus beta lambda 2, way up to the pth component is xp plus beta lambda p. Then rest of the components are all 0. And it is here you have precisely n minus p many zeros. So this vector u, it is n times one vector. Fine. And by n times one vector I mean it is a vector from Rn, n by 1 matrix it is. Let u and v similarly I am taking x1 minus beta times lambda 1, x2 minus beta times lambda 2, so on xp plus beta times lambda p. Then rest of them are all zeros. There are n minus p many here. Fine. If I am taking this u and v, then you notice the following. Then from the equation number 3, you have then 3 produce 3 implies a u is equal to b and also a v is equal to b, no doubt. And once you have this, we notice the following, and also you have x star is equal to half of u plus half of v. Is not this? Because if you just add this u and v, then the first component is 2x1, second component is 2x2, the pth component is 2xp, and rest of them are all 0. And therefore half of u plus v is nothing but this x star. X star is having x1, x2, xp as a component. And therefore what we are observing here, that x star is convex combination of u and u and v are satisfying au equal to b and av is equal to b. But here u and v, if we can prove that u and v components are all greater than equals to 0, then u v will be feasible solution. So you have then obtained two feasible points u and v such that the convex combination of u and v is the point x star. That will violate the assumption that x star is an extreme point. Fine. So here what do we have to prove? We have to prove that u is not greater than equals to 0, v is greater than equals to 0, and we will show that there exists at least one beta by which u can be made all components greater than equals to 0, v can be made all components non-negative. Fine. Because here you notice that this from 1 and 2, this equation 3 is valid for any u of beta, any beta greater than 0, and accordingly you are considering this u and v, right? So let me now show that there exists a beta greater than 0 for which u and v are feasible solution to ax equal to b and x greater than equals to 0. And therefore we need to show that the components of u and v are all non-negative for at least one choice of beta. That will prove the result that x star will be an extreme point. Fine. So let us show that below that u is greater than equals to 0 and v is greater than equals to 0. So how do we show this? You notice the following. So let me name this equation as 3a and this equation as 3. Fine. Let me name. Now from 3a and 3b, we observe that u is greater than equals to 0 and v is greater than equals to 0 if you have xi plus u is xi plus beta lambda I, the components greater than 0, and xi minus beta lambda I, the components of v are all greater than 0, or even you can take greater than equal to 0, no issue. So I'm just taking greater than 0 here for all I is equal to 1 to b. Fine. That is if now you will face three possible cases. What is the first? That you may have for a given I, for an I, for a given I equals to 1, say, you may have three possible cases. That you can have lambda 1 greater than 0, because you do not know what are lambda values. Here you have these lambda 1, lambda 2, lambda p are all real constants such that this equation 2 is valid. Lambda I is maybe positive, maybe negative, maybe 0 also. But at least one lambda I out of this lambda 1, lambda 2, lambda p is non-zero. Fine. So if lambda, so you will be into three cases. If lambda 1 is greater than 0, if lambda 1 is less than 0, if lambda 1 is equal to 0. You notice that if you are in this case, lambda 1 is greater than 0, then this xi plus beta lambda x1 plus beta lambda 1 will be greater than 0 if um, if you have just beta greater than 0. If beta is greater than 0, lambda 1 is greater than 0, xi is already, x1 is already greater than 0, so this component is greater than 0. So if lambda 1 is greater than 0, then you notice that xi x1 plus beta lambda 1 is greater than 0, no doubt, and you need beta to be, you need, if you want x1 minus beta lambda 1 is greater than 0, then you need to have beta less than x1 by lambda 1. Fine. In order to this second, for the first component of v greater than 0, if you have lambda 1 greater than 0, then beta has to be less than x1 by lambda 1. Fine. If lambda 1 is less than 0, then you notice that in order to realize x1 plus beta lambda 1 greater than 0, you should have beta less than x1 by lambda 1. Fine, minus lambda 1. If lambda 1 is less than 0, so here in order to realize that lambda, in order to realize that x1 plus beta lambda 1 greater than 0, you need to have, once lambda is less than 0, so minus lambda is greater than 0, you need to have beta not less than greater than, this is greater than this. Fine. And you need to have, and the second component xi minus beta lambda I is greater than 0, right? because lambda 1 is less than 0, so x1 minus beta lambda 1 is greater than 0, because beta is greater than 0 for any, because you are just choosing here beta greater than 0. So beta greater than 0 is restriction is already there. Together with, you need to have just beta greater than x1 minus lambda 1 in order to realize that both of these components are greater than 0. Fine. And then you don't need anything. So here let me write the following: that if lambda 1 is greater than 0, then take beta is in between 0 and x1 by lambda 1. That will give us both of these, x1 plus beta lambda 1 greater than 0, x1 minus beta lambda 1 greater than 0. If lambda 1 is less than 0, then take beta greater than x1 by minus lambda 1, and that will provide you both these, x1 plus beta lambda 1 and x1 minus beta lambda 1 greater than 0. Fine. So if you take like this, and for lambda equal to 0, then you don't need any restriction. You take any beta greater than 0, take any beta greater than 0, and that will give us x1 plus beta lambda 1 greater than 0 and x1 minus beta lambda 1 greater than 0, because x1 is non-zero and therefore x1 is greater than 0, because x star is a feasible solution. Fine. And so if lambda 1 is greater than 0, then take this. So therefore, if if the ith component is ith lambda I is greater than 0, then take 0 less than beta less than xi divided by lambda I. If lambda I is less than 0, then take this, beta is greater than this. And if lambda I is equal to 0, then take any beta. So therefore, let us try to find what possible value of beta all the components, that means for every I equal to 1 to p, both of these xi plus beta lambda I and xi minus beta lambda I, both of them will be positive. For that, we notice that for every lambda I which are greater than 0, for all of them you need to have beta lying in between 0 and xi divided by lambda I. Fine. So if let's suppose lambda 1 is positive, that is the real number line, this is 0 location, and let's suppose lambda 1 is positive, then you need to have beta more than 0 but less than x1 by lambda 1. Fine. Beta has to be in between 0 and x1 by lambda 1. Let me suppose lambda 2 is also greater than 0. Then the location of x2 by lambda 2 will be on the right hand side. So let me suppose here is my location of x2 by lambda 2. Fine. So beta has to satisfy both, that 0 less than beta less than x1 by lambda 1. Similarly, you also have to have 0 less than beta less than x2 by lambda 2. Then only the first two components of both of u and v, both of these two will be greater than 0, right? So beta has to be then in between 0 and then minimum of all this. So minimum of all xi divided by lambda I, where lambda I is positive. So for all lambda I greater than 0, you take beta has to be in between 0 and this. Fine. Now for negative, if you have lambda 1 negative, then in that case what will happen? The location of xi by lambda I, x1 by minus lambda I will be positive. Fine. And therefore what you require is that beta has to be greater than, so let me for the negative lambdas, let me write here 0, and here if lambda 1 is negative, then beta has to be bigger than this xi divided by lambda I, that means x1 divided by minus lambda 1. Fine. If lambda 1 is negative, if lambda 1 is negative, the beta has to be bigger than this, and if lambda 1 is positive, then beta has to be below this. Fine. So what you need to have, you consider all the locations of x1 by lambda 1, x2 by lambda 2, where this lambda 1 lambda 2 are positive, or you consider xi by lambda I for all lambda I greater than 0, and you also consider maximum of lambda I less than 0 xi by minus lambda I. Fine. And then you choose beta in between minimum and maximum of lambda I greater than 0 of this quantity xi by lambda I. You choose this. After choosing beta in between these two, you observe that is, if you choose beta in between maximum of lambda I less than 0 xi by minus lambda I less than beta less than, sorry, here it will be minimum, right? Lambda I greater than 0 xi by lambda I. Am I right? If my beta is in between these two, then all the components will be positive. All the components of u and v will be positive. Let me recheck once more. Lambda I, if it is positive, then I have this component positive, and to be this is positive, you need to have beta less than xi by lambda. All right, this is. Then for lambda I less than 0, if lambda I is less than 0, then you take xi greater than minus beta lambda I. So, but minus lambda I is positive. So if you are taking division, so beta is less than. I wrote earlier, right? That beta has to be less than this. Fine. So beta has also to be less than, not greater than here. Sorry for my calculation mistake. That. So let me write then both the things in a compact way. That it will be just like xi divided by modulus of lambda I, right? Because lambda is negative, and let me write this part equals to xi by modulus of lambda I. Then I don't have to discretize into for lambda I positive and lambda I negative, right? So here you just take, then here is 0 location, then you consider for non-zero lambda is you just consider to have this ratio x1 by modulus of lambda 1 is here, and beta has to be lesser than this quantity and greater than 0. So beta has to be 0 and less than all of this xi divided by modulus of lambda I, and therefore beta has to be less than the minimum value of all xi divided by modulus of lambda I for all I in between 1 to p with lambda I not equals to 0. Fine. And there exists such a beta because at least one of the lambda I is non-zero. Because at least one of these lambda 1, lambda 2, lambda p is non-zero. And therefore, there exists a beta in between 0 and minimum of this value. Fine. And hence, if you choose this, so choosing now beta in between 0 and minimum of 1 less than I less than p lambda I not equals to 0 xi divided by modulus of lambda I, you notice that u is greater than 0 and v is greater than equals to 0. By u greater than equals to 0, v greater than equals to 0, it is obvious that we mean all the components of u are non-negative, all the components of v are non-negative. Fine. And therefore what happens? Therefore now here let me name it as 4 and 5. So 4 and 5 implies 4 and 5 implies that x star is half of u plus half of v, where u v are two feasible solutions. Fine. And then this is contradictory to x star an extreme point, which is contradictory to x star a x star an extreme point. Fine. And why you are arriving to a contradictory step? This is due to your assumption that if possible let a1 a2 ap is linearly dependent, due to which you had the equation number 2. Then from the equation number 2 you could construct the equation number 3, and from there entire thing went wrong. Entire thing like went wrong means you are arriving to a step which is contradictory, right? This is due to your assumption, and therefore this set a1 a2 ap cannot be linearly dependent, and hence it is linearly independent. Now once a set is linearly independent and where the vectors in the set are from the m-dimensional Euclidean space, then obviously the number of vectors in this set is less than equal to m, because any set of more than m vectors of Rm is linearly dependent. Fine. And hence you have p less than equals to m. If p is equal to m, then x star is a basic feasible solution. Why basic feasible solution? Because if p equals to m, then this matrix capital B you just take, then take capital B as this matrix a1 a2 ap, which is a matrix of order m by m whose columns are all linearly independent. Therefore capital B is an m by m submatrix, non-singular submatrix of the matrix capital A. Then take this, which will produce x star as a basic feasible solution, because you have b times x star is equal to small b, right? Because you have a1 x1 plus a2 x2 plus ap xp is equal to b. You have this a1 x1 plus a2 x2 plus ap xp is equal to b. This is equivalent of capital B times x star is equal to small b, right? And therefore x star is a basic feasible solution. However, if p less than m, if now p less than m, then apply the extension theorem, then do the following. Let me write it neatly. Then since A is full rank, that means the rank of A is equal to m. A is having rank m, therefore we can extract m minus p column vectors from A which are not in B, not in this set A1, A2, AP, which together with the set, by which I mean we can extract this m minus p column vectors. So these m minus p column vectors together with this set A1, A2, AP form a basis of Rm, or form a matrix non-singular matrix B. I am writing once again B, or B bar, say, consisting of first first few columns are A1, A2, AP. Then you are extracting this m minus p columns from A. Without loss of generality, let us suppose those m minus p columns are AP plus 1, AP plus 2 till AM. If those are not AP plus 1, AP plus 2 and AM, then you interchange the role of the variables, and then you will obtain that these m minus p column vectors from A, which are not in this A1 to AP, and therefore you are choosing these m minus p column vectors from which vectors? From this AP plus 1, AP plus 2 till AN. So out of these n minus p vectors, here are n minus p rest out vectors which are not there in this set A1, A2, AP, but these are there in the matrix capital A. So out of these n minus p columns of capital A, you can choose m minus p column vectors from A by the extension theorem, such that those m minus p column vectors together with this set A1, A2, AP will form a basis, will form a non-singular matrix B bar given by A1, A2, AP together with those m minus p column vectors. Without loss of generality, I am assuming those m minus p vectors are just first m minus p vectors of these n minus p vectors. Fine. If not, then you interchange the role of the variables. You replace the variable x100 with xp plus 1, and accordingly you are interchanging the name of AP plus 1 and A100. So interchanging the role of the variable means you are interchanging the names of the columns, corresponding columns of the variables, right? And then there is a non-singular. You can construct the non-singular matrix capital B such that you have now B bar X star is equal to small b, because you just take in X star, after the pth components all are zeros, and for the first p, a1 x1 plus a2 x2 plus apxp is already equal to b, and therefore from here what will you get? X star is a basic feasible solution. The equation will produce b bar X star shows that X star is a basic feasible solution, and that is what you wanted to prove, right? And this way, corresponding to this basic feasible solution, the non-singular submatrix m by m submatrix of the matrix capital A is B bar, right? Now this ends of the proof of an extreme point is a basic feasible solution. It is a very long proof, and not only long proof, several steps requires understanding of neatly the notions, this LD, linear dependence, linear independence, basis, extension theorem, and replacement theorem. Please have a look of them. Then only you will be neatly able to understand this theorem. And now I feel you will need a book to follow, so that at any step you are missing out the logic that I have spoken here, then you can look the book several times and you will be able to understand on your own, because all of you are very matured by now, I guess. You are all fourth year students. Once you are fourth yearites, therefore you on your own is have grown enough to understand something, to read and learn on your own. Obviously I am here to help you out. So any doubt if you are still having with this proof, you please have a look once more, and then if you are still facing at some line of the proof that I have written and spoken here, you come to my doubt clearing class. I will be conducting doubt clearing class very soon, and on those doubt clearing classes you are always welcome to discuss any amount of time, any particular notion or particular line if you are having problem. Fine. So with this, let me now end of the lecture here. On the next day I will start discussion of fundamental theorem of linear programming problem, from where I will start the method, the simplex method to solve a linear programming problem. Thank you all for all of your kind presence.